In this video, we will be reviewing over stereoisomerization. Now, stereoisomers are molecules that have the same molecular formula and sequence of bonded atoms, but they're different in their three-dimensional orientation of those atoms within space. Now, this is going to be different from structural isomers, which share the same molecular formula, but the bond connection or the order of the atoms will be different. So by definition, molecules that are stereoisomers of each other will represent the same structural isomer. So here we have just a typical isomer. Now remember that an isomer has the same molecular formula but a different structural formula. So as we look at isomers, we have to look at them in pairs. Here we have butane and here we have isobutane. And if we look, they each have the same number of carbons. In this case, that's going to be 4. And then when we look at the number of hydrogens, they have the same number of hydrogens. In this case, we have 10. And so the only difference that we see between butane and isobutane is that structurally they have different shapes. Now, because they have different shapes, they will have different chemical makeups, different properties, and thus they make themselves two completely different chemical compounds. So as we look at isomers, constitutional isomers are isomers that have the same molecular formula but different names. So as we look at this isomer 2-methylpentane versus 3-methylpentane, the difference we see is the location of the methyl group being on carbon 2 versus carbon 3. Stereoisomers, on the other hand, are the same molecular formula, the same name, except a prefix will be added to the name. Now this is due to the fact that on both of these cyclopentanes we have 2 methyl groups. In the first structure, we have both methyl groups coming out from the cyclopentane, where in our second structure we have the first methyl group coming out from our cyclopentane and then our second methyl group going back deep into the screen. So it's behind the structure. So just reviewing over the difference between structural isomers and stereoisomers. Structural isomers can also be called constitutional isomers. They have the same molecular formula but different structural formulas. That can be in the form of chains. Here we have a chain of 4 carbon atoms, and we'll know that by the 4 black dots. And the white will represent the hydrogens. Now on both of these chemical compounds we have 4 carbon and we have the same number of hydrogens. The only difference we see is here we have it as a chain, where here we have it as a T-shaped structure. We can also have structural isomers dealing with the position of a specific compound or a specific element. Here we're going to be using the green ball, and it can represent any number of chemicals. And we'll notice how it comes off of carbon 1 on our first chemical compound, and it comes off of carbon 2 on our second chemical compound. Again, both chemicals have the same number of black balls representing the carbon, the same number of white balls representing the same number of hydrogens, same number of green balls representing an unknown chemical. The only difference is the location of the green ball being on carbon 1 here and on carbon 2 here. We can also have structural isomers relating to functional groups. Now, in this particular example here, we have a chemical compound that has 2 carbons, and it's got our 5 hydrogens here. Here it's attached to an oxygen attached to a hydrogen. So this right here is an OH group or an alcohol, where here we have the same number of hydrogens. We have 6 hydrogens, just as we had here. We have 2 carbons, just as we have here, but you'll notice that the 2 carbons are separated by an oxygen, and that makes this chemical compound an ether. And so while we have the same molecular formula, because of those structural differences, we have completely different chemical compounds with completely different chemical properties. Now, when we look at stereoisomers, we have the same molecular formula, but the atoms will occupy different positions in space. Now, these are a little bit more difficult to deal with, and when we think of stereoisomers, it's a good idea to go ahead and purchase a cheap chemical molecule set so that you can put the chemical compounds together, or to download an app that allows you to take your chemical compounds and to rotate those into space. With our stereoisomers, with regard to geometric isomers, this occurs due to the restriction of a rotation of a double bonded carbon compound. And what we mean by that is here we have two carbons and they are attached at a double bond. This double bond prevents our carbons from rotating within space. And so because of that, this would be a set form. It could not change and twist into any other form. And so here we have an example where both of our chemicals are on the same side, where here we have it where we have one on one side and one on the other side. And so we deal with this with prefixes known as cis and trans. We can also look at stereoisomers with regard to optical isomerization. And this occurs when molecules have a chiral center. And we'll talk to you about what a chiral center is in the future slides. But generally what we're looking at is two chemical compounds that cannot be superimposed upon one another. And so geometric isomers and optic isomers are examples of stereoisomers, and we'll be spending the remainder of this video reviewing over and understanding the difference between the two. We will begin with geometric isomers. Again, geometric isomers are going to deal with a double bonded carbon compound. And this double bonded carbon compound is such that these carbons are not allowed to rotate within space. And because these two carbons are fixed and unable to rotate, that will set up our chemical compound to be in a very stable set. And we will notice two forms. We'll notice where we have the green chemicals on opposite sides from one another, and we'll notice that when we have the green compounds where they'll be right on the same side of one another. Now, when we have a group where we have the chemicals on the same side, and I do want to stop and say that when I'm talking about the chemicals, it can be the same, so these could be chlorines, or we could look at this being a chlorine molecule and this being an iodine molecule. But we notice that both of these are on the same side of the double bond, and so we use the prefix cis in our name. So we would name the chemical compound, and then we would have the prefix cis in front of it. Trans, on the other hand, have the groups of atoms on opposite sides from one another, and so again we would name the chemical compound, but we would use the prefix trans. Again, the reason for our cis-trans setup is because this carbon double bonded to the carbon have a restricted rotation, so the groups on either side of the bond are frozen in position, and that means that these carbons are not able to flip and rotate up and change positions. So this produces two possibilities. We can have a possibility where we have those atoms on the same side of the double bond, or we can have a condition where we have those atoms on opposite sides of the double bond. So the two structures cannot be interchanged easily, and they occupy different positions in space. Therefore, they are completely different chemical compounds with different properties. Now, reviewing over the cis-trans, again notice that right here we have that double bonded alkene, that double bonded carbon, and here we would have, say, a bromine, and here we have a methyl group. And you'll notice that both of these, while they are not identical, both of these structures are on the same side of the double bonded carbon, and so we use the prefix cis. In this situation, we have our methyl group on one side, we have our bromine on the other. They are across from one another with regards to our double bond, and therefore we use the prefix trans. Do note that these atoms here do not have to be identical. We're just talking about their location with regard to the multiple bond. In this example, the atoms are identical and they represent a methyl group, a carbon with 3 hydrogens attached, and they are on the same side of the multiple bond. So we have the prefix cis, where here we have one on this side of the multiple bond, one on this side of the multiple bond, and therefore we use the prefix trans. So this right here would be a transbutane. Optical isomers deal with when we have a chiral center, meaning that the pair of isomers cannot be superimposed upon one another. What this means is that while everything has a mirror image, the mirror image may not be superimposable. For example, our left hand and our right hand are not superimposable on one another. Therefore, we would say that our hands are chiral. Now, if we have a molecule that is superimposable, then we say that it is achiral. Do be careful because the terminology sounds the opposite of what they are. Not superimposable means we have a chiral compound. Superimposable means we have an achiral compound. So here we have the left and right hands, both being examples of a non-superimposable mirror image, both being chiral. All molecules that have a mirror image, but in some cases the molecule is the same molecule. Now here we have 2 examples of fluoromethane, and what I mean by this is if we compare these, it appears that we have 2 different chemical compounds. However, if we rotate these around, you will notice that this will rotate to this position, this will rotate going back, and therefore we have the fluorine coming out and the hydrogen going back in. Now to help understand whether you have the same chemical that has been rotated or do you have a mirror image, it is helpful to use those molecular models and to put the model together and to visualize moving the molecule around in space. If you cannot have one of those molecules, then you can download many different apps and work with the apps to rotate your chemical and to determine is it a mirror image or is it the same molecule. Here we have lactic acid, which causes milk to sour, and lactic acid, which causes soreness in muscles. Now, this one right here has a negative in front, this has a positive in front, and what that means is that these are 2 different chemical compounds. And if we look at this, if we take this methyl group and we rotate it around, moving it over here, you'll notice that when we move this rotated over, our hydrogen will move back and our carboxyl group here will move to this position. Now that would not be the same as this chemical compound right here. And so because these are 2 different chemical compounds and they are not superimposable on each other, then we say that these compounds are chiral. Let's review that statement one more time. Here we have 2 chemical compounds, and the black will represent carbon, and you'll notice that we have 4 different chemical compounds attached to the carbon. Now notice where the yellow is located versus the yellow here. Now if we take this yellow and we were to rotate this over, when we rotate that over, this would rotate back around to being located right here, and our green would be located to the back. And so no matter how we rotate this chemical compound, we can never rotate this chemical compound to where it matches up to this chemical compound. Therefore, these 2 structures are not superimposable, and therefore they are chiral. This usually happens when a molecule contains a carbon atom with 4 different groups attached to it. We say the compound is chiral and the compound is asymmetric. So we call these type of chemical compounds chiral and optically active. These chiral compounds, these optically active compounds, are called enantiomers. And so we can distinguish our enantiomers by using prefixes such as the plus and minus, or the D and the L, or more correctly, the R and S system. And so if we have a chemical compound that is not superimposable, it has a chiral situation, it is optically active, it is called an enantiomer. If we have a chemical that is superimposable, it is achiral and it is called a diastereomer. So we have a pair of chemical compounds sitting in front of us. We would like to ask a series of questions. Do these chemical compounds have the same molecular formula? If they do not, they are not isomers. If they do, then yes, they are isomers. Are the molecules the exact same name, except they have a prefix or a suffix? If no, then we classify them as constitutional isomers. If yes, then they are stereoisomers. Are they superimposable? If yes, then they have a chiral complex and they are called enantiomers. If no, they are not superimposable, then they are achiral and they are called diastereomers. So again, looking at the difference between the terminology of chiral versus achiral. If we had a mirror in front, then we look at our left hand. Our left hand would not be superimposable on our right hand, and therefore this would be a chiral object. However, if we look at a ball and the ball is identical with the object itself, it is superimposable. Therefore, the ball would be an achiral object. On this slide, we want to look at and consider several molecules to determine whether or not they are chiral or whether they are achiral. Here we have the water molecule, H2O. We have the mirror image. Now when we line these up, you're going to notice that the bonds align. And because they do align and they are mirror images, water is achiral. Now here we have CH2BrCl. And so when we place this up to the mirror and we rotate the bonds, we will notice that when we rotate this that they will line up. And so in order to rotate this, what we need to do is take this and rotate this up and around, and we're basically flipping this molecule. And when we flip that molecule, it will match up to this right here. And so because we can rotate these molecules and we can align the bonds and they're lined up, this is also an achiral molecule. Now the reason that the previous two molecules were achiral is because single covalent bonds can easily rotate. And so what appears to be completely different structures really are not. And so it looks like it, but due to the way that the structures are written out, we can easily rotate bonds around and line them up. Now when we align a molecule up, we can have a plane of symmetry. And this means that the molecule can be divided in half and have two identical halves. So if we can do this, the molecule is achiral. If we look at a molecule and there is no plane of symmetry, then the molecule is chiral. So what exactly does this mean to us? First off, chiral molecules often react differently with other chiral molecules, and this is like the idea that a right hand does not fit into a left-handed glove. The molecule must be the correct shape to fit the molecule it is reacting with. And many natural molecules are chiral, and most natural reactions are affected by optical isomerization. For example, most amino acids are chiral, along with a lot of other molecules. And in nature, only one optical isomer occurs. And it may be either the left rotation or the right rotation relating to light. And many drugs are optically active, with one of the enantiomers only having the beneficial effect. Now, this was very clear in the 1960s with the thalidomide, and this was given to pregnant women. And because of that wrong optical isomerization, this led to many disabled babies being born missing limbs. Now we can also see how this relates with lemons versus oranges. And so we can see that an S form gives us the taste for a lemon, while the R form gives that taste for an orange. So in summary, the basic principles of chirality is that everything has a mirror image. The fundamental question is whether or not the molecule and its mirror image are superimposable. If they are superimposable, then the molecule is called achiral. If the molecule and its mirror image are not superimposable, then the molecule is chiral. We also look at the presence or the absence of planes of symmetry. The presence of a plane of symmetry makes the molecule achiral. The absence of the plane of symmetry makes the molecule chiral.